Imagine sitting at a local cafe, typing your credentials into a banking application. You see the lock icon in your browser and you feel secure. But what if an adversary sitting 3 tables away from you is capturing every single byte of your plain text traffic without ever touching your device? They haven't hacked the bank, they haven't compromised the Wi Fi password at the cafe. Instead, they have exploited a fundamental trust flaw that's built directly into how local networks access and discover hardware. By exploiting this flaw, an attacker can silently position themselves in the exact middle of your connection. Before we can look at the code or deploy a defense, we have to look at the catastrophic failure state of an unverified network. Let's look at how local devices talk to each other and why they blindly trust total strangers. So let's talk about ARP. ARP stands for Address Resolution Protocol, and it is the system that your device uses to connect IP addresses to local hardware addresses or MACs. To understand how this vulnerability works, we must look at the local network's routing primitives. When your computer wants to send data across a room, it uses 2 distinct identifiers: your MAC address and your IP address. So, an IP address, or Internet Protocol address, is a logical, temporary network labeled address to route data across from different networks globally. A MAC address, on the other hand, or Media Access Control address, is a permanent, unique physical footprint that is burned directly into your device's network hardware and is established by the manufacturers. You can think of this like an apartment building. The IP address is the apartment number, so it tells you and the mailman where to drop off letters. But once inside the building, the delivery worker needs to match that apartment number into a physical, unique nameplate or key slot to actually drop the mail in. That physical nameplate or key slot is your MAC address. So on a local network, computers communicate using ARP. Um, ARP is a logical protocol and it's designed to map a known logical IP address directly to a physical MAC address on a local area network. So here's the fundamental rule of ARP technology, and it is that ARP is completely stateless and entirely unverified. So if we go through it, we'll talk through the process of how the protocol works. So when your computer wants to talk to the router, it shouts out to the entire room, hey, who has the IP address of, let's say, for example, 192.168.1.1? Please tell me your physical MAC address. The protocol is built on absolute trust, so it expects that only the true owner of that IP address will reply. And even worse than that, it accepts ARP replies even if they were never asked for in the first place. So it has a lack of verification and it shouts out to anyone and just expects the right person to reply. And this lack of verification is the structural flaw that we'll try and exploit today. So we'll look under the hood to watch this mechanism step by step. We'll trace the inputs to the outputs to observe the exact moment where the network state is compromised. So first, let's examine the victim's current legitimate network state. Okay, so notice the mapping here. The gateway router at 192.168.1.1 maps safely to the physical MAC address that ends in 4455. The attacker's machine at 192.168.1.99 maps to the EEFF MAC address. So now let's execute an exploit from the attacker's terminal, and we do this using a packet crafting tool. Alrighty, so we've executed our poison ARP spoof. So the attacker is now sending forged, unsolicited ARP response frames directly to the victim. So these frames are explicitly saying, hey, The IP address is 192.168.1.1 has moved. Its new physical hardware address is my MAC address, which is AABBCCDDEEFF. All right, simultaneously, the attacker sends a reciprocal lie to the router claiming to be the victim. Because ARP is unverified, both the victim and the router blindly accept these updates and they overwrite their memory caches. So let's verify the cache manipulation by running the exact same command on the victim's machine now again. Alrighty, look closely at the screen and you can see that the IP address of the gateway router 192.168.1.1 now points directly to the physical MAC address of the attacker. The victim's operating system has updated its internal lookup table. So from this exact point forward, every packet intended for the external internet is encapsulated and forwarded directly to the attacker's network interference card. So the attack is complete now, and you can see how silent and highly effective it can be. So understanding this mechanism means security professionals stop treating local networks as inherently secure zones. So in enterprise and production environments, we cannot rely on endpoints to protect themselves. We must enforce security directly at the hardware boundaries, the network switch. So the industry standard mitigation for this vulnerability is DAI, or dynamic ARP inspection. So dynamic ARP inspection is a security feature inside of enterprise network switches, and it validates the ARP packets by cross-referencing them to a trusted database before it forwards them on. So the switch achieves this by monitoring DHCP assignments, which is dynamic host configuration protocol assignments, and this is how this is a database of verified IP to MAC pairings. So the DHCP assigns the pairings, and the switches store a verified database of these pairings and cross-references these. So by executing these configuration commands, we can activate data validation rules on the switch hardware. So if an attacker attempts to send an unauthorized ARP frame and tries to change a neighbor's table, we can inspect that packet. It can identify within the switch that the MAC address does not match the assigned IP address that they have in the trusted lookup table, and then it will drop the frame at the physical port level, and it won't get forwarded on and changed. So to summarize the lesson today, ARP spoofing exploits the inherent lack of source verification in stateless networking layers, and it tries to manipulate logical address tables. And this is a vulnerability that is entirely mitigated by validating physical frames against trusted binding databases at the switch architecture boundary. So, a question to test your mastery, or even a challenge to go look at and learn about yourself, because I think you can get a lot out of looking things up and discovering things yourself. And that is, if an organization utilizes fully static IP allocations across their architecture and it completely disables DHCP, how must dynamic ARP inspection be configured to ensure that untrusted frames are still accurately validated and dropped? So leave your solutions, command structures, or analysis in the comments, and thank you for watching.